All right, today's lesson is a continuation of similar figures, but this time we're going to be looking at section 11.6, proportions related to volumes of similar figures. So here we have two cones, and we are going to, again, assume that these cones are similar. It says right here, knowing that these cones are similar. We're going to look at their radius lengths compared to their volume measurements, and we're going to see how those compare as a proportion or similar figure ratios. So, first question says, what is the radius of the large cone? So, the large cone is the one on the right, and if I look at the radius, that is a length of 12 units long. The radius of the small cone is the one on the left, and that is a length of 8 units long. So, we're going to create a ratio, the large radius compared to the small radius. If I divide that out on my calculator, I can see that comes out to 1.5 as the scale factor. All right, now when I compare volume, it's a little bit more complex. We're going to have to reach back into our memory to figure out how do you find the volume of a cone again. So remember, volume of a cone is pi times radius squared times the height of the cone divided by 3. So for the large cone, our height is 21, and the small cone, the height is 14. So I'm going to do pi times 12 squared times 21 divided by 3 for the large cone. Now I am using the pi button. Times 21 divided by 3. Okay, now unfortunately when we use the pi button, it comes out to a really terrible decimal and it can't get a precise answer. So what I'm going to do instead is I'm going to just do the numerical part and then I'm going to attach the pi onto the end. That will help eliminate any ugly decimals. This is called writing in exact terms or in terms of pi. So when I multiply all of those parts together, 12 squared times 21 divided by 3, I get 1008, and then I attach the pi. So this would be 1008 pi cubic units. If I look at the small cone would be pi times radius squared times the height of 14 divided by 3. Again, to avoid those ugly decimals, I'm going to do 8 squared times 14 divided by 3. Unfortunately, that itself comes out to an ugly decimal. Jeez Louise. So I'm going to have to give it a decimal approximation here. Luckily, this comes out to a repeating number. So it comes out to 298.6 repeating, and then I'll put the pi on. And again, those are cubic units because we're looking at volume. So now when I compare a ratio of the large cone to the small cone, we would have 1008 pi divided by 298.6 repeating pi. Now because we have pi's in both of those, the pi's can cancel. Then I can type in my numbers, 1008 divided by 298.6 repeating, and trick my calculator to do repeating, I put a lot of sixes in there on my calculator screen, and this comes out to 3.375. Now, I'm not really seeing a comparison between 1.5 and 3.375. But if I think back to how we did the area comparison, let's say that this was in centimeters for the radius, this would be centimeters cubed for the volume. So when I look at those units, I can see that the centimeters is not the same as centimeters cubed. So I need to force it to be the same. So if I take those 1.5 centimeters and I cube it, it comes out to 3.375 centimeters cubed. So when we're looking at a comparison between side length, perimeter, ratio, or radius, height, all of those singular units like centimeters, if I want to compare them to a volume, they need to become cubic before we can compare it. Or vice versa, we could take the cubic units and uncube them with a cube root to create just plain units. So this brings us to the proportional volumes conjecture. And it says if you compare edge lengths or radius or heights of two similar figures, these would be 3D figures, they would compare like edge to edge or height to height or radius to radius, but their volumes would compare in that same form to the power of 3. Now, remember when we were doing those area ones, we took that power of 2 for the area comparison and we squared both numbers. So remember, when you have an exponent of 3, it does get distributed to both of those terms in the fraction. All right, so this is going to help us solve for missing values when we're looking at maybe a height compared to a volume. All right, again, this is confusing, so remember that we will have to make sure that we have all the same units before we can cross multiply to solve our proportions. Example 1. The right cylinders next to here are similar, and it says little radius is 10 centimeters. The volume of the large cylinder, so volume is 64 centimeters cubed, and the volume of the small cylinder is 8 centimeters cubed. We are missing big R, which would just be in centimeters. So here I do want to compare them using a proportion. So I'm going to first look at the radii. So I have 10 centimeters compared to our unknown centimeters. Then we're going to set that equal to the volume comparison. And the volume is 8 centimeters cubed to 64 centimeters cubed. Okay, now we are looking for the radius. So we are trying to get just plain centimeters. So there's a couple different ways we can go about doing this. We can uncube the current cubic measurements, or reverse that, we could cube the regular centimeter measurements, and then in the end, we could uncube the results. Now, 8 and 64 are really nice numbers to take the cube root of, but sometimes you're going to come out with numbers that are not. So I'm going to show you both methods on how to solve this. The first way is I would take the 10 over r and I would cube it. So I would say 10 cubed over r cubed is equal to 8 over 64. Now 10 cubed, I really can change that. 10 to the power of 3 comes out to be 1,000. That'll be easier to look at. And then we're going to cross multiply. So 1,000 times 64 comes out to 64,000, which is equal to the other direction, 8 times r cubed. All right, I'm going to do a little t-chart. Got to get rid of the 8, so I'm going to divide by 8. 64,000 divided by 8 comes out to 8,000, and that is equal to r cubed. Now, many of you might not have used the cube root button before, so you might take a little bit of time to try to figure out where it is on your calculator. On my calculator, I'm using a TI-84 Plus, and it's a graphing calculator. I actually have to do a couple of steps to get the cube root. I have to hit my math button that's on the left. Once I hit that, it's like the fourth option down. It looks like this with a cube root. So I'm going to choose that option and then put in the number that I'm trying to cube root. For others of you who are using a more scientific calculator, you're going to look for your square root button, and then somewhere near there, there's probably going to be a button that has an X in front of that square root. For those scientific calculators, you're going to want to make sure that you put the 3 first, then choose that button, which might be a combination of buttons, and then you'll type in the number that you're trying to cube root. So we are going to apply the cube root of 8,000. This means what number cubed equals 8,000. So if I do the cube root of 8,000 on my calculator, my radius comes out to be a length of 20 centimeters. So that big cylinder is a radius of 20 centimeters. All right, now I told you I was going to show you both methods. So I need to save myself some space here. I'm going to erase this just so I have some space. I'm going to show you the other method, which is taking that 10 over r and 8 over 64 and first doing the cube root on the 8 and the 64. So if I do the cube root of 8, it's saying what number cubed equals 8. It actually comes out to the number 2. And if I do the same thing on the number 64, it comes out to the number 4. And then I can compare 10 over r to 2 over 4. My multiplying here is going to be a lot easier. 10 times 4 is 40. 2 times r is 2r. Little mini t-chart, divide by 2. And my radius still comes out to be, a measurement of 20 centimeters. So it just depends on when you want to do your cube root and if the numbers come out nice. This one, they happen to come out really nice. All right, let's try example 2. Example 2 says, given these two similar cylinders, find the volume of the small cylinder. All right, so I have a height and a radius, and then just a radius. So let me think here. I could do proportions to find the height, or I could find the volume of the large one and use the radii compared to the volumes and do a proportion as well. That would deal with cubic numbers. So maybe I'll try that since we're trying to do cubic numbers in this one. So let's remember volume formula for a cylinder, pi times radius squared times height. On our first larger cylinder, I can see that the radius is 14 and the height is 42. All right, now again, if I use the pi button, I'm going to get some ugly numbers. So I might want to use 3.14, or I might just want to keep it in terms of pi because I know that eventually the pi's are going to cancel each other out. I don't know. I think I'm going to use 3.14 instead. 14 squared times 42. All right, so my volume for the large cylinder comes out to be 25848.48. 25,848.48. It doesn't have a units on here, so I'll just say units cubed. All right, I'm going to compare the radiuses together. So I'm going to do 14 units compared to 10 units. And then I would compare the volumes together. 25,848.48 units cubed over unknown units cubed. Okay, now in this case, I'm looking for the cubic units. So it makes sense to cube these items before I cross multiply. If I uncube the current cubic units, then I'm going to have to recube them to find the cubic units for the missing volume. All right, here we go. 14 to the power of 3 comes out to be 2744. 10 to the power of 3 comes out to be 1,000. I'm going to rewrite that long volume over here, which is 25,848.48 units cubed over unknown units cubed. Now, technically, I could put units cubed here because I did cube those numbers. So all of my labels are now the same, so now we just cross multiply. So 25,848.48 times 1,000. Ooh, these numbers keep growing. 25848. Oh, did I screw it up? 848480. I think I got that right. Let's see here. Oh, that's a big number. 25,848,480 is equal to the other direction, which would be 2744 times x. All right, little tiny t-chart says divide by 2744. And my X number, which is my unknown volume, comes out to 9,420 units cubed. So the volume of that smaller cylinder is 9,420 units cubed. All right, let's try our next example. On this next example, we have cones this time, and it says that they are in fact similar cones. And it says find the volume of the small cone. So this volume is unknown units cubed. The volume over here isn't listed, but we can calculate the volume of a cone by using the formula. So that formula is pi times radius squared times height divided by 3. So if I plug in those numbers, pi times 6 squared times 10 divided by 3, again, I think I might use 3.14 just to make things a little bit easier to read off my calculator. And when I use 3.14, my volume comes out to be 376.8 units cubed. All right, now on these particular pictures, the only thing they have in common is the height. So what I'm going to do is I'm going to compare the height of the large cone in units compared to the height of the small cone in units. And then I'm going to put the volume comparison. 376.8 units cubed compared to, unknown units cubed. All right, now again, we are looking for the volume, units cubed. So it just makes sense to make everything cubed. So I'm going to cube my heights. All right, 10 to the power of 3 is 1,000 again. 5 to the power of 3 is 125. And then I'm going to keep the other fraction because that one is already in cubic units. Then all of our units will be cubic. We can cross multiply. So 125 times 376.8. Calculator error. Boy, I'm struggling. 125 times 376.8. Some sticky buttons here. Always double check your buttons that you're pressing in. Comes out to 47,100. And if I go the other direction, cross multiplying, that is 1,000 times x. So a little t-chart, divide by 1,000 on both sides. Divide by 1,000. And I get an answer of 47.1. And this would be the volume, cubic units. So volume 47.1 units cubed. All right, example 4. Given these two similar pyramids, calculate the height of the larger pyramid, knowing that the volume of the larger pyramid is 256 cubic units. So I'm just going to write that down, 256 units cubed. I don't know the height, so I'm going to put an H for height. And over here on this one, I do see that I have a height, but I don't have a volume. Fortunately, this is a right triangular based pyramid, so I can do the formula for volume using the measurements given. Little base times little height divided by 2 times big height divided by 3. All right, plug those in. 6 times 9 divided by 2 times 12 divided by 3. 6 times 9 divided by 2 times 12 divided by 3. All right, this volume for the smaller pyramid comes out to be 108 units cubed. So now I've got both volumes. I can compare those in a ratio, and then I can compare the heights in a ratio and make a proportion. All right, so I'm going to start with the one on the left, the smaller one, 108 units cubed compared to 256 units cubed. That's going to be equal to, now I got to use the heights. So this is 12 units compared to unknown units. Okay, now this time we are looking for the unknown plane units, not the cubic one. So I could uncube or cube root the current volumes and then cross multiply. Or I could cube the height units, cross multiply, and then uncube them. I think this time I'm going to see if doing the cube root of those numbers is going to come out to a nice value. So I'm actually going to uncube or cube root these volumes. So I'm going to do my buttons for cube root 108. Oh dear, it comes out to a terrible decimal. But you know what? I'm going to give it a try. 4.762, we'll say. And then I'm going to do the cube root of 256. Ugh, 6.3496. I did one extra decimal there because then I didn't have to round it weird. All right, then I've got 12 over here and H, and then we'll cross multiply. All right, now luckily I have that long 6.3 blah, blah, blah number in my calculator, so I can just hit times 12. And that comes out to 76.195-ish. If I go the other way, it would be 4.762 times H. So we'll divide by 4.762 on both sides. Divided by 4.762. Now, I did round that 4.762, and so my final answer comes out to kind of an ugly number on the calculator, but it is almost exactly 16. So I'm just going to round it to the whole number 16 and say that this height is 16 units long. All right, last example. Here it says, given these two similar rectangular prisms, calculate the missing volume of the small prism if the large prism volume is, I'm going to write it down, 17,472 units cubed. Now we are missing this volume, so I'm going to put volume is unknown units cubed. Fortunately, we have the height of each rectangular prism, so we can compare their heights. 18 units compared to 24 units, to the ratio of their volumes, unknown units cubed, to 17,472 units cubed. But because we are missing the volume, cubic units, we're going to make sure that we cube everything else to get them all to be the same cubic units. So here I'm going to do 18 to the power of 3. That comes out to 5,832. 24 to the power of 3 comes out to 13,824. And those will be equal to the unknown volume over 17,472. Now we can cross multiply because these would all be cubic units. So multiply diagonally. Oh, that's a large number here. 101,896,704 is equal to, and then I'm going to go the other direction, 13,824 times x. We'll do a tiny little t-chart. We'll divide by 13,824. And that will get us our x measurement, which is the unknown volume for the small rectangular prism. And it comes out to 7,371. So our volume for the small rectangular prism is 7,371 units cubed. And that concludes our lesson today, looking at the proportions or ratios of volumes and similar figures.